Okay, ladies and gentlemen, divisibility rules. Our objective to use divisibility rules to determine prime factorizations. One question you may have is, why study divisibility? Well, it turns out that divisibility is going to help in problem solving, and it's going to be very important when we learn factoring. So problem solving, also factoring. We'll take a look in just a minute at a problem involving divisibility. What does divisibility mean? Well, if you're going to study the rules about it, you want to know what it means. Divisibility goes like this. A first number is divisible by a second number if when we divide the first by the second, the remainder is blank. What goes in the blank? Think about it. Okay, hopefully you put in the number 0. Hopefully that's what you thought about. Let's take a look at an example. Here it says, is 20 divisible by 5? Well, here's our first number. Here's our second number. We're going to divide the first by the second. If we take 20 and we divide that by 5, is the remainder 0? Well, we know 5 times 4 is 20. Multiply 20. Subtract, we get 0. And since the remainder is 0, the answer, yes. Let's take a look at the next one. Is 20 divisible by 6? Well, again, we divide the first by the second. Here we're going to take 20, and we'll divide that by 6. Well, we know we can count 3 6s out of 20. 3 times 6 gives us 18. When we subtract, we're going to end up getting 2. What's our remainder? It's not 0, so the answer here would be no. So simple divisibility examples. Now, it turns out that there are divisibility rules that make these kinds of problems very, very straightforward to do. That's what we're going to take a look at in just a moment. Let's take a look, though, at a real-world example of a divisibility problem. Why don't you take a moment, read that through. Ladies and gentlemen, by knowing divisibility rules, you can do a problem like this in probably around 3 seconds. Let's go ahead and take a look at our divisibility rules. We'll come back to this problem shortly. Now, it turns out that there are many divisibility rules. The common ones are for 2, 3, 4, 5, 6, 8, 9, 10, 11, etc. We're going to only focus on 2, 3, 5, and 10 to keep things simple here and to keep things short. But you may want to examine the other divisibility rules as well. Let's take a look. Some of this you probably already know, which could be very helpful. You may want to pause from time to time. You may want to take notes. You may want to, when we get to problems, pause the video and try to do the problems and then check and see how you do. Let's take a look at our 4 rules. A whole number is divisible by 2 if, what do we put here? Well, hopefully you were thinking about the fact that it's got to be an even number. In other words, it ends in one of these digits, 0, 2, 4, 6, or 8. That's divisibility by 2. What about divisibility by 3? Divisibility by 3 has a completely different rule. Let's take a look at that. It says a whole number is divisible by 3 if, and this is sort of an unusual rule, the number formed by the sum of the digits is divisible by 3. Or a shorter way to say it is if the sum of its digits is divisible by 3. We're going to take a look at this rule closely, and all of these actually, in just a little bit. Let's take a look at the next one. Whole number is divisible by 5 if, you should know, it's got to end in what? 0 or 5. The final one, a whole number is divisible by 10 if it ends in 0. Let's go ahead and put these rules to work. What I've got lower here is a chart with divisibility practice. And what we want to do is we want to take a look and see if any one of these red numbers is divisible by 2, 3, 5, or 10. And as we take a look right here, what I'm going to do is I'm just going to use a Y for yes. Let's go through the number 12. Well, by just knowing your multiplication tables, you probably have a good idea of what the answers are. But I'm going to use the divisibility rules above right here. Is 12 divisible by 2? Well, as we take a look, it's got to end in a 0, 2, 4, 6, or 8. 12 definitely ends in a 2, so the answer is yes. Is 12 divisible by 3? Well, let's look at our rule. What do they say? It says the sum of the digits is divisible by 3. And this is a little bit unusual. Usually in math, you don't do this. But what we do in this particular problem is we look at the digits, 1 and 2, and we add these up. 1 plus 2 gives 3. Now, is this divisible by 3? You bet. You can divide 3 by 3 and get a remainder of 0. So the answer, yes. Isn't that a strange rule? Let's take a look at the next one. Is 12 divisible by 5? Well, our rule is it's got to end in a 0 or 5. And this obviously ends in a 2, so the answer, no. I'll put N for no. How about 10? Well, for 10, it's got to end in a 0. This does not end in a 0, so the answer, no. I want you to go ahead and try these next on your own. So pause the video, give that a try. Okay, let's take a look at this next one. For 18, is it divisible by 2? Well, our rule for 2 is we look at what it ends in. And so here it ends in an 8, and that matches this. So the answer is going to be yes. Is it divisible by 3? Well, let's add up the digits here. Remember, that's our rule for 3. You got to do it this way for 3 if you're using the divisibility rule. What's 1 plus 8? That gives us a 9. Is 9 divisible by 3? You bet it is. And if 9 is divisible by 3, so is 18. What about 5? Well, it's got to end in a 0 or a 5, and that's a no. 10 is a no as well. Okay, what I want to have you do is I want to have you try these next two on your own. So pause it, give that a try, please. Okay, let's take a look at this next one. In fact, let's do both of these together. Divisibility by 2. We check the last digit to see if it's even. Here it's a 5, so that's going to be a no. However, here it's a 0, that'll be a yes. Next one, let's check divisibility by 3. What do? Let's add up the digits. 6 plus 5, we know, 6 plus 5 right here is 11. And does 3 go into 11 evenly? Well, if you do 11 divided by 3, you're not going to get a remainder of 0, so the answer there is going to be no. Let's check 30. 3 plus 10 is 3, and this is divisible by 3. If we divide this by 3, we get a remainder of 0, so it's yes. The next one, divisibility by 5. Well, it's got to end in a 5 or a 0, and this ends in a 5, so it's yes. The 30 ends in a 0, so that's yes. The last one, divisibility by 10. Well, it's got to end in a 0 according to what we have here, and this does not, so it's a no. This does right here end in a 0, so it's a yes. All right, ladies and gentlemen, I want you to try the last two. So pause it, give those a try. Okay, let's take a look at the last two and see what we've got right here. We'll take these together right here. We'll take divisibility by 2. This one right here ends in a 0, so yes. This one right here does not end in a 0, 2, 4, 6, or 8, so that's a no. Let's check divisibility by 3. Add 5 plus 1 plus 0, we get 6. 3 goes into 6 evenly, so that's a yes. Let's add all these digits up. 5 plus 8 is 13, plus 5 is 18. 3 goes into 18, so it's also going to go into 585, so that's a yes. Divisibility by 5. Hopefully you got yes for both. Divisibility by 10. Hopefully you got a yes there because it ends in a 0, and a no for the last one. All right, divisibility rules. Now that we've practiced those just a little bit, let's do some problems involving these rules. Here it says, we'll use divisibility rules to factor numbers completely. Basically, we're going to find what's called the prime factorization, and we'll use factor trees here. Let's take a look at prime numbers just very briefly. Ladies and gentlemen, I want you to see if you can remember the prime numbers. See if you can list out the first 6 or 7. Give it a try. Pause the video. Okay, let's take a look. Hopefully your prime numbers started with the lowest number of 2. Then we have 3, 5, 7, 11, 13, 17, 19, and the list goes on and on forever. Now, what we're going to do is use these prime numbers. By the way, one thing you may be thinking is are prime numbers only used in math problems? And the answer to that is, well, if you even use a cell phone, you may be familiar with the fact that often data is what's called encrypted. And prime numbers are used in encrypting data. And so prime numbers, they have all kinds of applications like that. But that may be something that you're curious about looking up. Let's take a look here. Here it says factor completely, use a factor tree. One thing we know is that anytime that you have a number, if it's not a prime number like one of these, then you can actually factor it down to primes. Let's take a look at 35. We know this ends in 5, so for sure 5 is going to be a factor of 35. How many 5s can we count out of 35? 7. Now, when we factor, we always stop when our bottom number of the tree is prime. Both 5 and 7 are prime numbers right here, so we can stop. 35 we can write as 5 times 7. We'll be using this kind of a skill when we factor. I want you to go ahead and try number 2 on your own. Pause it. All right, let's go through number 2. As we look at problem number 2, one thing we realize is that this ends in an even, so definitely we could factor out a 2. And 28 divided by 2, if you divide that out, we would get a 14. Now, we're going to stop with the 2 because 2 is prime. It's up here. And you always stop with your prime number. How about 14? Is 14 prime? Look up here. It's not prime, and so we can keep going further. This ends in a 4, so we know that 2 is a factor of 7, and it will be 2 times 7. And now look, all the bottom numbers are prime numbers, 2s and 7s, 2s and 7s. So we can say 28 is 2 times 2 times 7. With exponents, we can write this as 2 squared times 7. Let's take a look at problem number 3 similarly. With number 3, well, this ends in a 0, so definitely 10 goes in. And we can say 30 is 3 times 10. But 3 is prime, so we stop. Let's try to break down 10. Well, 10 we know is 2 times 5. And so 30 is going to be 2 times 3 times 5. And notice usually you're going to write your factors here from smallest to greatest. All right, I want you to go ahead and try number 4 and number 5 on your own. So pause it, give those a try, please. Okay, let's take a look at problem number 4. Here we have 48. Well, if we think back to our divisibility rules, one thing that we know is it ends in an 8, so 2 is going to go in. And 48 divided by 2 gives us 24. 24 ends in a 4. That's even, so 2 is going to go in. 2 times 12. 12 ends in an even, so we know 2 goes in, 2 times 6. And 6 gives us 2 times 3. So on our tree, we're going to end up having 2 multiplied 4 times a 3. And we'll write that here as 2 to the 4th times 3. Let's try number 5. With number 5, what we've got right here is 135. It ends in a 5, so we know that 5 goes into 135. 5 is a factor of that. And if we take 135 and we divide that by 5, we're going to end up getting what number? Well, it should end up being a 27. So 135 divided by 5 is 27. Now, one question you may have is, wait a second, how do we get to 27? We know this ends in an even, so we can use a 5. Well, one way to get it is to take 135 and divide that by 5. Just the regular way. How many 5s can we count out of 13? There will be a 2. Multiply 2 times 5, 10. Subtract, we get a 3. Bring down the 5. Now we divide again. How many 5s can we count out of 35? It's going to be a 7. Subtract, we're going to get a 0. So let's go ahead and work with the 27. We know 5 is a prime because it's right up here as one of our primes, but 27 will not be. If we add up the digits, we obviously see 2 plus 7 is 9, so 3 goes in. It'll be 3 times 9, and 9 is 3 times 3. Now, because I ran out of space here, I'm going to put the answer down here. We have 3 3s, so we'll write that as 3 to the 3rd power, or 3 cubed, times a 5. Last one, 180. Well, what would be a factor of 180? Definitely 0, because it ends in a 0, tells us that 10 is going to be a factor that we can use. And so we can take 180, and because 10 is a factor, we can write that as 18 times 10. Now use what we know about the multiplication table. And so we have a pair of 2's, which gives us a 2 squared. We have a pair of 3's, which gives us a 3 squared. And then we also have a 5. So prime factorizations. Okay, ladies and gentlemen, as the last thing, let's go back to our problem with Sandra. Earlier, we mentioned that a problem like this, you should be able to do pretty quickly. Sandra has $171 to buy gifts for her 3 best friends. Can she split $171 into 3 equal whole dollar amounts? Well, as we think about it, we want to go ahead and if we're going to split something into equal amounts, we're talking about what operation? Add, subtract, multiply, or divide. Most students would say that we're going to try this and we're going to see if we can divide this by 3 and find what kind of an answer we would get. Well, as you take a look at this problem carefully, does 3 go evenly into 171? Is 171 divisible by 3? Well, let's add up the digits. 1 plus 7 plus 1 gives us 9. And does 3 go evenly into 9? You bet. And so, because it goes evenly into 9, we know that the answer is yes, according to our divisibility rule. Now, what's very interesting is this. Suppose that Sandra was wealthy, and suppose that this problem involved not $171, but $1,710. Does that change our answer? Well, the 0 doesn't change the total of 9, so the answer would still be yes. And you can have all kinds of fun with this sort of divisibility rule. Why don't we stop right there? Ladies and gentlemen, hopefully this has been helpful, and good luck with your math.